For this last lab, I decided to look at the physics of a ballerina's leap. I wanted to see if the ballerina's leap could be accurately modeled by a model of projectile motion using fundamental principles. I also wanted to explore how much force she used to push off from the ground, which I was able to find from my data. I also found that I was able to model my data pretty accurately using the model of a projectile motion. I made several assumptions before starting my lab. I treated the ballerina as a point particles to simplify my model. I chose this because I had no way of knowing certain values like drag. I also assumed that in this short amount of time, drag would have very little effect on the ballerina, so the previous assumption wouldn't affect my data very much. I used a video of Misty Copeland doing a leap. I found it easier to use a video of a well-known professional because I was able to find her measurements and different values I needed online. I tracked her center of mass, which I approximated to be around her belly button. Because it is a little difficult to click this exact point every time due to her rotation of the torso, and the fact that the human body isn't a perfect system, my data is a little bit messy. As you can see, she is moving in an arc, which is why I thought it would be possible to use a model of projectile motion to model her motion. I used a combination of different codes that we had previously done in the class to set up my model. Because I am considering a point particle, I model the ballerina with a ball. I input the mass, which I found online, and my initial position and velocity, which I took from my tracker data. The initial velocity was found by calculating the change in position versus time between my second and third data points in tracker. I wanted to compare the position data from my model to my data, so I input my data points into the code with a CSV file. Because I am neglecting drag force from my model, the net force consists only of the force of gravity, which is just the mass of the ball multiplied by the Earth's gravitation, or g, in the negative y direction. Next, I set up the equations for the components of the net force. I did this by using the equations for the components of the change in momentum over time, whose values are equal to the components of the net force. Here you can see that F net equals the change in momentum over time. The F net parallel is equal to the change in momentum over time parallel, which is calculated here, and the F net perpendicular is equal to the change in momentum over time perpendicular, which is found by subtracting dp dt parallel from the total dp dt. I then use Newton's second law to update the change in velocity and position inside my loop. I also added in the equations for the energy principle here. Here I solve for the change in kinetic and potential energy. This will allow me to see if the energy in the system is conserved. Here are the equations for the energy principle, and here they are in my code. Now I will run my code. The yellow arrow shows the net force, the black arrow shows F net parallel, and the magenta arrow shows F net perpendicular. As you can see, the parabolic motion of the model does a fairly accurate job of matching the motion of my data. The graph on the left shows the red being the position of my data versus the blue being the positions of my model. The slight difference in shape could be due to my assumption of the point particle because the model is over-predicting the motion, which would be possibly corrected if all the other forces acting on the ballerina were considered. When I run the code again to look at the energy graph, this is what we get. When we look at the energy graph of the model on the left, we can see that energy is conserved, because the green line representing total energy is showing zero change in energy. The blue line is showing the change in kinetic energy, which represents the ball slowing down towards the top of the arc and then speeding back up in the opposite direction. The red line shows the change in gravitational potential energy, which increases towards the top of the arc and then decreases as the ball comes back down towards the ground. Essentially, this graph is showing us that parabolic motion is just a zoomed-in version of the motion of oscillations. When trying to find the force that the ballerina pushed off with, I looked at my tracker data. I used the equation force equals mass times acceleration to be able to find the force she pushed with. I found that from my data, the acceleration could be approximated as 20 meters per second squared. When I multiplied this by my mass of 50 kilograms, I found that the force is 1,000 newtons. This value makes sense because that means that she is pushing off with about twice the force of gravity, which I found to be 490 newtons. In conclusion, it was possible to model a ballerina's leap with parabolic motion using a simple system. However, a more detailed system may provide a more accurate result. Using my knowledge of fundamental principles, I was able to explore the energy conservation and the force the ballerina leaped with.